Welcome to your video on entropy. Entropy is a really interesting aspect of our universe. And what you might, if you've heard of it before, you've probably heard it described as disorder. And so you can say, hey, I don't want to pick up my room. My room is just experiencing an increase in entropy, and that's how it is. But that is not exactly how thermodynamically entropy is defined. So let's talk about what entropy means and how people started thinking about it. So when we first started thinking about this in about the 1870s, people were like, okay, some stuff just happens, and then some stuff you actually have to put in energy, you have to work on it to make it happen. And they thought about this in terms of a ball rolling down a hill. You put a ball on a side of a hill, it will roll down. It will go from high potential energy to low potential energy. And we call something that we don't have to put extra work into spontaneous, versus the ball would not just roll up the hill. That is not spontaneous. You would have to roll it up like Atlas, right? And so they hypothesized in those 1870s that all chemical reactions that release energy should also be spontaneous. You're taking things with higher PE into lower PE. Now, they didn't really know about transition states at this point, right? We know that you have to put in energy to then get back out energy. But this still kind of holds true. Reactions are more likely to happen when they, without humans having to do anything, when they release energy, right? Once we ignite this reaction to take oxygen and hydrogen gas to form water, we get tons of energy out. We don't have to keep working on it. But there are some reactions that we have to keep working on. Specifically, when we reverse this reaction, you can take water, run an electric current through it. You're putting in enough energy to break apart the bonds in these water molecules, and they will go back and form this. Not spontaneous though, okay? And so what people started thinking about, they're like, wait a minute. When we dissolved that citric acid, that process got cold, but I didn't have to do anything. I just put the two things together. So we come to this question of, why do some reactions happen spontaneously but get cold, require a net input of energy? Oh my gosh, what are we going to do? So this takes us to the idea that there must be something else going on. So we figured out that entropy, actually, someone named Boltzmann figured this out, that the entropy of the universe is always increasing. So something that's interesting, you think about the universe, it's always expanding. We always have more space. There are increasing number of possibilities. The letter we use to signify entropy is S, which is nice because it's different than every other letter. So, as long as things are going with the universe, they can be spontaneous. If you fight the universe, you're going to have to put in work. So, what we need to be able to do to think about entropy and whether it's increasing or decreasing, whether we're going with the universe or not, is we actually have to qualitatively think about what types of situations have more or less entropy. So, let's practice. We are going to practice with a nice little mini chessboard here, okay? So imagine we have three pieces. Here are my random pieces. I have a cork, I have these little black cubes, and I have this bolt right here. Okay, so we have these three items, and they have three possible positions, and then they can be in different spots. Okay, just like atoms. They have different positions that they can be in, but there are only so many combinations, right? And there aren't that many combinations. I don't know if I've done any of these again, but I think you can see, hey, there are only so many options, and then you've repeated all of the options. So a way to think about entropy is the number of options, or what they call microstates, available to the particles that you're talking about in chemistry. So let's imagine we put these three things on a much, much bigger chessboard. Okay, they could go here, 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 right? They could go here. They could go here. There are so many spots for these things to be. So the more states available to your particles, or even the more particles you have, right? If we start adding in some other random things from the desk here, okay, what else can we get? We're going to start having more possibilities for where things can be and how they can be in relation to each other. So I just really increase the entropy by putting in more particles, meaning there are more relationships between these particles. It's like, oh, I'm by this pin, I'm by this sodium atom, but I'm way over here or I'm way over here. We've increased all of the options. So this demonstrates an increase of entropy. And you're like, okay, Ms. Brown, checkerboards are great, but I don't know if I can apply this to chemistry. I'm not quite sure. So let's practice. Let's see what we can do here. Let's look at some options. Okay, so the first one we're going to look at is solid versus liquid versus gas. So think about solids. Do the particles within a solid move in relation to each other? No, right? They're locked into place. They're crystalline. They are perhaps in a lattice. I don't know where my lattice went. I had a nice one. I lost it. We have a nice lattice here. They're not moving in our sodium chloride, right? They just vibrate a little bit. So are these going to move a lot? Do they have a lot of options? No, not really. Not that much, okay? So then when we look at something, say in the liquid phase, okay? So they're kind of moving around each other. They're also turning in place, okay? Are they moving a whole bunch though, compared to a gas? Not quite, right? But they are moving more. So there are more available positions, right? Because they're rotating, they're changing in a liquid than in a solid. Let's think about a gas. These are flying all around, they're bumping into each other, they're moving. These have, not only are they rotating, not only are they vibrating like the solid and the liquid, they are moving translationally, and they can also have options of different speeds. So that even increases the entropy. It increases the differentiation between these particles because some are going really fast, some move slow, they bump, they change their speeds. So gas has the highest entropy of our three phases of matter. Okay, so things are tending to become more gases. Kind of interesting. Let's look at small volume versus large volume. This works with our chessboard idea too. So if we have three, let's say we have a gas and we compress it down into a small container. So think about anything you have in like an aerosol can, any sort of gas that's just compressed. So when it has smaller volume, there are just fewer places for the particles to be than in a larger volume. So which between these two has the higher entropy? Well, I hope you picked larger volume. Another thing we can compare is same volume, but fewer things versus lots of things. So the more things you have, will that be more entropy or less entropy? Well, more entropy, more possibilities, more options, more things changing, okay? So finally, how does entropy play into this idea of dissolving? Well, in the lab, we dissolved citric acid, okay, and we'll model it here. We dissolved citric acid and it got colder. So why would it actually happen? So let's think about this. Let's imagine we just have, this can just be our example solid, sodium chloride, okay? Does a solid like this have a lot of entropy? No, because these are all kind of locked in place. It's like, well, I'm kind of stuck here. I don't have a lot of options to be different, okay? And the water's all attracted. It's kind of hanging out. So then what happens when we dissolve is these are able to be in solution and they get to be more mobile, right? So they're surrounded by these water molecules, but they're also moving throughout the solution. So instead of being locked down like they were in the lattice, they're able to translate and move throughout our solution. So they have increased their entropy. So things will dissolve. If you mix it, does it help? Oh, sure, because that puts in the energy to break this stuff up. But if you just let it set, things will dissolve up unto a certain point because you're increasing the entropy and you are going with the universe. So what did we learn? We learned that some things can be spontaneous. So don't confuse things being spontaneous with being quick though. Rust forming on iron is spontaneous. It just takes a long time, but we don't have to do anything. It will happen. It's increasing the entropy of our system and increasing the entropy of our universe. Okay, we learned that we use the letter S to signify entropy, and that if we want to go against, if we want to reduce the entropy of a system, we're going to have to put in work. And that's not just like Rihanna work, it's like science work. You have to put in force over distance to do that work, okay? And then finally, we learned that entropy tells us why things dissolve even if they get cold.